Hello everyone, this channel is talking about bulk materials. Today's video is number 5. Today's topics for equation of wall thickness calculation for ASME B31.1 and temperature dependent of parameter Y. First, we will review the previous video number 4 talked about the equation of wall thickness. It was understood that the equation of the wall thickness calculation, which was based on thin-walled cylinder model modified with factor beta equals 0.6, has been used on the standard such as ASME section 8 division 1 and the ASME B31.1 under the condition of K ratio. Outside diameter to inside diameter 1.5 or less. And the equation of the wall thickness calculation based on the Rame's equation has been used in the standard in case of K larger than 1.5. The modified equation was introduced into the basic circumferential stress equation based on the thin-walled cylinder model with adding coefficient factor beta. The basic circumferential stress equation, sigma y equal PD bar 2t, is modified to sigma y equal P parenthesis D plus 2 beta T parenthesis bar 2T. So in the parenthesis term, D plus 2 beta T is the inside the diameter indicated partial increasing the inside diameter. Originally the inside diameter D, but pressurized to the thin-walled models, cylinder model, is expansion the cylinder model and increasing the inside diameter. So continue to the pressurize, finally through the cylinder model the burst. That at that time inside diameter D surely the increasing the inside diameter D. So we will introduce the correction factor beta in D plus 2 beta T is the virtual inside diameter indicated. It was understood that the modified equation with the substitution of beta equals 0.6 was matching the actual burst test data and also the both of the modified equation for thin-walled cylinder and Rame's equation match perfectly under the condition of K 1.5 or less. Sigma 1 equal P parenthesis D plus 2 beta T parenthesis bar 2T. This is converted into the wall thickness equation T equal PD bar denominator understanding. So sigma 1 minus P beta. In case of beta equals 0.6, the equation of wall thickness calculation based on the inside diameter D in the standard as follows. So this equation is same as that, like this, based on the circumferential stress by the thin-walled cylinder model. Beta equals 0.6 assigned. So ASME B 60.34 for the valve but body wall thickness equation B1 is indicated here. T equal 1.5 times PC. PC is assigns a rating class number, and D is the inside diameter, and denominator terms stress is assigns a constant value 7,000 assigned, and minus 0.6 PC is a rating class. This is ASME B16.34 wall thickness calculation equation. So ASME Section 8 Division 1 and ASME B31.1, it's this standard same as the basic equation like this, same as. The equation of wall thickness calculation based on the outside diameter of the piping component is standardized in ASME B31.1, converting into the equation with the outside diameter dO is as follows. T equal P dO outside diameter, and the denominator two parentheses S is the allowable stress plus 0.4 P parentheses. So in case of the convert to the outside diameter dO based equation, so beta factor is beta minus 1.0. So minus 0.4, 0 minus minus, so changing the plus. So in case of the outside diameter dO, beta beta area is 0.4 changing these numbers. So in case of K 1.5 or less, this is a thin wall thickness calculation. So the temperature below 900 Fahrenheit, this is a Y equal 0.4, and no axis welding. So we have to use the seamless pipe and no casting pipe. If we use a casting pipe, so we consider about the casting quality factor, F, something considered. Following equation is a general setting for the wall thickness calculation in ASME B31.1. This is B31.1, the wall thickness calculation equation. So P, the Tm is the minimum wall thickness. P is the inlet pressure equal design pressure. dO is the outside diameter piping. And denominator to parenthesis S. S is the stress occurred. But normally standard equation is assign the maximum allowable stress for each materials and also temperature. So E is the weld joint efficiency, and W is the weld strength reduction factor. So in case of we use the casting pipe, we consider the casting quality factor F. So normally we think about the seamless pipe. So seamless pipe we used. So E and W is 1.0. So only term is stress level S, maximum allowable stress level think. So one factor is normally the usually is beta minus 1.0, but B31.1 assigns the y values. Y coefficient having values as given in table 114.1.2-1 using y instead of 0.4. So correction factor y equals 0.4 is used up to temperature of 900 Fahrenheit. Coefficient y varies with 0.5, 0.7 according to the temperature above 900 Fahrenheit. So we look at the table 104.1.2-1 value of y derived from ASME B31.1. So horizontal axis indicated the temperature. Temperature is a relatively high temperature region. So and the material is type of material, ferritic steels. Ferritic steel is such as carbon steel, low alloy steel, chromium, molybdenum alloy steel, and multi-synthetic stainless steel. So ferritic steel indicated the Y factor, Y value is 0.4, 900 degree Fahrenheit and below. And next high, 50 degree Fahrenheit high, 950 degree Fahrenheit temperature, Y factor changing to 0.5. And next high, 50 degree Fahrenheit, 1000 degree Fahrenheit temperature, Y factor changing to 0.7. And temperature 1000 and more still assigned 0.7. Austenitic steel. Austenitic steel is mean austenitic stainless steel. Typically, austenitic stainless steel is 304 SST, 316 SST, or 321 SST something. So in case of austenitic stainless steel, so Y factor equals 0.4 up to the 1050 degree Fahrenheit. So Y equals 0.4 and below, temperature below and below 0.4. And next high 50 degree Fahrenheit high increasing 1100 degree Fahrenheit temperature, Y equal 0.5 changing. And next 50 degree Fahrenheit increasing 1150 degree Fahrenheit, Y factor 0.7 changing. And continue to the 0.7, the increase in the temperature. So nickel alloy is UNS number L06690. This nickel alloy is Y value is assigned same as austenitic stainless steel, same as. And another nickel alloy is N0617, N08800, N08810, N08825. Four kind of nickel alloy assigned together same Y values. So Y value is the temperature up to the 1150 degree Fahrenheit. Y values are assigned 0.4 and increasing the 50, next increasing the 50 degree Fahrenheit, 1200 temperature, Fahrenheit temperature, Y factor changing the 0.5, and next 50 degree Fahrenheit, increasing 1150 degree Fahrenheit change. 0.7 change to be Y factors. In case of the intermediate temperature, example 970. 970 indicate nothing the number, so we have to calculate the Y value with the interpolated method. 0.07 and 957 1000. So general note A, the value of Y may be interpolated between the 50 Fahrenheit incremental values shown in the table. So general note B, for pipe with a D0/Tn ratio less than 6, the value of Y for ferritic and austenitic steels designed for temperatures of 900 Fahrenheit and below shall be taken as Y equal D bar parenthesis D plus DO parenthesis. Later we will discuss about that meaning of the general note B. So in accordance with table 104.1.2-1, Y equals 0.5 at 950 Fahrenheit and Y equals 0.7 above and 1000 Fahrenheit are assigned for ferritic steel, carbon steel and chromal steel and martensitic stainless steel. Y equals 0.5 at 1100 Fahrenheit and Y equals 0.7 above and 1150 Fahrenheit are assigned for austenitic steels, austenitic stainless steels, 304, 316 SST. So we are looking why the coefficient Y varies according to the materials and temperature. So this page is indicated wall thickness calculation equation derived from ASME B31.1. So this equation is for minimum wall thickness pipe calculation equation. So straight pipe under internal pressure, seamless, longitudinal welded or spiral welded. Minimum wall thickness. The minimum thickness of pipe wall required for design pressure within the prescribed temperature limit for materials permit by para 1 to 3.1, including the allowance for mechanical strength, shall not be less than the determined by equation 7. So in the equation, the A is the allowance, additional thicknesses. Normally we think about A is the corrosion allowance something. Tn is the minimum required thickness, and P the internal pressure, the internal design pressure. DO is the outside diameter pipe, and denominator S S is the allowable stress. E is the welding joint efficiency. W is the weld strength reduction factor. So normally think about the allowable stress, including joint efficiency or casting quality factor here. So maximum allowable stress in the internal pressure and joint efficiency. And in case of the casting pipe, casting quality factor to be considered. So W, the weld strength reduction factor, equal 1 for seamless pipe or for seam welded pipe operating below the clip wrench. So Y factor equal this. Y factor is a coefficient having values as given in table 104.1.2-1. So we discuss about the wall thickness calculation for the thick walled pipe in ASME B31 point. So we talk about the general note B comment. In accordance with the general note B in table 104.1.2-1 for pipe with a DO bar TM ratio less than 6. The value of Y for ferritic and austenitic stainless steels designed for temperature of 900 Fahrenheit and below shall be taken as Y equal D bar parenthesis D plus DO parenthesis. So DO bar TM less than 6 this. So TM is indicated outside diameter minus inside diameter divided 2. So therefore convert into the following. So substitute this equation into the TM. So the simplify the equation like this, and dO bar D is meaning the K ratio. K equal dO bar D ratio. So 6 bar 4 larger than 6 bar 4th equal 1.5. So K equal dO bar D larger than 1.5. That indicate that shows the question the piping is something thick wall pipe is to be considered. Therefore, it is understood that the description of note B is for the thick-walled pipe. When the value of K increasing with K equal 1.6, K equal 1.7, K equal 1.8, etc., the related pipe will become thicker, and as a result, the value of Y equal D bar parenthesis D plus DO parenthesis can get Y equal 0.38, Y equal 0.37, Y equal 0.36, etc. with decrease of number. It is understood that Lamma's stress equation is applied on the thick-walled vessel in case of K larger than 1.5 in ASME Section 8 Division 1. However, the equation of wall thickness calculation which is based on the thin-walled cylinder model, is still used on the thick-walled condition in ASME B31.1. Comparison of the rate of sigma 1 bar P between the result of Lamar's equation and the result of thin-walled basis equation with increase of k value is shown in below table to confirm to match the Lamar's equation. We can confirm the coincide between Lamar's equation and thin-walled basis equation with thick wall in case of k equal above 1.5. So comparison of the calculate sigma 1 bar P between Lamar's stress equation and the equation of thin-walled cylinder model. So upper table is K equal ratio DO bar D. So 1.5 and 1.6, 1.7, 1.8. So increasing the K ratio like this. So Y equal D bar D plus DO, or changing the Y equal 1 bar denominator parenthesis K plus 1 parenthesis. So Y factor is K equal 1.5. So Y equal obtain the 0.4. K equal 1.6. Y equal 0.38. K equal 1.7, Y equal 0.37 is calculated obtained in this number. So beta number, beta equal 1 minus Y. So K equal 1.5 in case of K equal 1.5, beta equal 0.6. So K equal 1.6, beta equal 0.62, 0.63, 0.64. It calculates the beta factor like this. So stress term sigma 1 bar P equal like this equation. So I like this equation is introduced. So this substitute the K number into the K and beta into the number beta into here. So calculate the number is like this, calculated. Also, none of the equation, the stress term, sigma 1 bar P, also B bar A equal K factor. So calculate the number, so something. So to compare the ASME B31.1 Lamar's stress equation is completely same number, same values calculated. So we can confirm the constant between Lamar's equation and thin-walled basis equation with thick wall in case of K above 1.5. So ASME B31.1, the wall thickness equation is based on a thin-walled simple model equation, but thick piping area is also also use the same equation. It is okay. So next, we will discuss about why was coefficient y introduced into the calculation of the pipe wall thickness in ASME B31.1. Allowable tensile stress is applied on the minimum wall thickness calculation as below. Tm equal PDO bar denominator 2 parenthesis SEW plus PY parenthesis, where S indicates allowable tensile stress. This allowable tensile stress is determined accordance with its safety factor of the tensile strength below the clip temperature and clip rupture test results in the high temperature clip region in the ferritic steels. The profile of the allowable tensile stress against the varied temperature is normally shown in the attached figure in right side. This figure is indicated the allowable stress temperature curve. So horizontal axis indicated the temperature unit Fahrenheit, and the vertical axis indicated the allowable tensile strength. So we call allowable stress. So orange line is indicated the allowable stress temperature curves. So blue line is before safety factor assigned 1/4 of tensile strength up to the 1998. So now currently assign the safety factor of 1/3.5 of tensile strength in the current. The allowable stress curve is like this, current allowable stress like this profile. So the high temperature area dominated to the clip rupture test data. And initially assigned the clip test data is not changing from here now, not changing. So still assign the same data. So safety factor of the tensile strength is changing 1/4 to 1/3.5. So I drawn the two allowable stress values are drawn here. So that this curve is indicated normal temperature. Some things normal temperature indicated allowable stress values are constant. But this temperature is 850 degrees Fahrenheit. Rapidly increasing the temperature, rapidly decreasing the allowable stress values. Very rapidly decrease. And this is a normally profile of the allowable stress curves. It is known that the allowable tensile stress is rapidly decreasing in high temperature clip region. It is assumed that the calculated minimum wall thickness is much increased according to the decrease of allowable stress value which is rapidly decline in the high temperature creep region. According to the article number 1, reference here, it is said that the equation T equal PDO bar denominator 2 parenthesis S plus 0.4 P parenthesis. This is initially introduced for wall thickness calculation was initially introduced in the standard in the 1950s. Also, it is said that after that, expansion into the high temperature region was considered and significantly increasing of the calculated thickness was concerned for thermal stress. Therefore, coefficient Y was introduced into the equation for wall thickness calculation as T equal PD0 denominator 2 parenthesis S plus P introduce the Y factor. The coefficient Y, which was introduced into the equation for wall thickness calculation, so coefficient Y varies according to the materials and temperature. It is suggested that the establishment of the allowable strength for P22 pipe depends on the tensile strength multiplied by 1 3.5 up to temperature 850 Fahrenheit, and on the creep rupture test data temperature 900 Fahrenheit or more by the allowable strength temperature curve. So that the same figure like this. So 850 Fahrenheit, the allowable tensile stress is determined by introduced safety factor of tensile strength multiplied 1 3.5 below and 850 like this. So this is the inflection point. So temperature increasing, the rapidly decreasing the allowable stress due to the creep rupture test data based. So this point is 900 Fahrenheit or less is Y equal 0.4. This point 900. And next 50 Fahrenheit increasing, temperature increasing at 950 Fahrenheit, Y equal 0.5 changing. And next increasing of the 50 degree Fahrenheit temperature 1000 Fahrenheit or more, Y equal 0.7 changing like this. So this is table 104.1 to -1 fatigue steels. 900 and below Y equal 0.4 and 950 50 degree Fahrenheit increasing, changing the Y factor equal 0.5, and the next higher 50 Fahrenheit 1000 Fahrenheit 0.7, and on more temperature continue to the Y equal 0.7 assigned. This chart is compare of the Y factor, changing the Y factor, and calibration thickness, how changing the profile. So, as assumption of the calculation condition, TM equal PDO by 2 sigma A plus PY seamless pipe used. So welding efficiency, joint efficiency, or weld reduction, strength reduction factor, or casting factor is not concerned. Only consider about the allowable stress values. Internal pressure, design pressure P equal 7,000 psi. Outside diameter DO equal 5 inch. Material 2.25 chrome 1 molybdenum steel SA335 P22 seamless pipe. Allowable tensile stress sigma A assigned from ASME Section 2 Part D 1998. Safety factor 1/4. Safety factor force. So this P22 the calculated curve 900 Fahrenheit. The Y factor is 0.4 here, and not changing. Y equal Y.04 still assigned to the high temperature area. The blue line indicates the calculated thickness. So huge calculated thick wall in the high temperature area. So we have something concerned about the thermal stress. So initially the ASME concerned about high temperature areas, something to decrease the calculated wall thickness, something thinking, consideration. So Y equal 0.5, Y equal 0.7, Y equal 0.8, Y 1.0. So Y factor is increasing the Y factor. So calculated thickness at the high temperature area is decreasing the calculated wall thickness. So Y factor equal 1.0 is something tremendous decrease of the wall thickness, but something concerned of the burst problem for the pressurized. So that so good point is something to be considered. So ASME some verification to be considered and assigned. And finally, Y factor equal 0.7 is assigned for high temperature area. The 0.5 is mitigate value assigned. So we understanding the Y factor changing, the tremendous reduce the calculated wall thickness in high temperature areas. It is understood that increasing the value of coefficient Y can decrease the wall thickness in high temperature region. In accordance with Table 104.1.2-1, coefficient y equal 0.4 is used up to temperature of 900 Fahrenheit, and y varies with 0.5, 0.7 according to the temperature above 900 Fahrenheit. It was supposed that y equals 0.7 was finally applied in high temperature region after some considerations, and y equals 0.5 was assigned on the way to y equals 0.7 to mitigate the rapid change of the calculated wall thickness. So this chart is compare the y factor 0.4 and y factor 0.5, y point equals 0.7. Changing the y factor is the calculated wall thickness is how changing. So blue line indicated y equals 0.4. So even if the high temperature area, we have to use the y equals 0.4, still use 0.4, increasing the calculated wall thickness is increasing. But located on the midway, y equals 0.5 located, and mitigate the rapid changing. So y equals 0.5 located between 900 and 1100. So 950 located at the y equals 0.5. So 1000 temperature or more, y equal 0.7 assigned. So this line like this. So we understanding the y factor 0.4 is a relatively lower temperature, 900 Fahrenheit in case of the ferritic steel, P22, and increasing the 950 Fahrenheit, increasing the 50 deg Fahrenheit, y equal 0.5 assigned. And next high temperature 50 deg Fahrenheit, increasing 1000 Fahrenheit temperature, changing the y equal 0.7, and still assign the y.77. That's calculated thickness profile against the temperature, like this profile. So now we discuss about here where is the starting point of creep region on the in the allowable stress temperature curve. It is understood that the temperature-dependent curves of allowable stress for P22 pipe material, which are indicated in both cases of tensile strength multiply 1/4 and tensile strength multiply 1/3.5, show that the start temperature of the creep region is 900 Fahrenheit at the branch point. So there's a branch point here. 3.5 curve and 1/4 curve. So decline here. This is a branch point. So indicated that we easily understand this point. This temperature is the start temperature of creep region. So allowable tensile stress is determined by based on creep rupture test data over 900 Fahrenheit from here. 900. Since the data of allowable strength in ASME are represented at every 50 Fahrenheit, it is assumed that the temperature increased by 50 Fahrenheit from the inflection point here is equivalent to the starting temperature of creep region in the temperature dependent curve of allowable stress. So this chart is a schematic diagram for the allowable stress temperature curve for ferritic steels. So ferritic steel is governed by the tensile strength multiply 3.5 and creep rupture test data. So allowable stress value is dominated by the tensile strength multiply 3.5 for normal temperature area. In a high temperature area is creep rupture test data dominate to the allowable stress values. So ASME is 50 Fahrenheit incrementally data plotted. So not continuous. So continuous the tensile strength value and creep rupture test data value is this is an intersection point. But ASME the actual allowable stress value is not indicated the intersection area between the tensile strength and the creep rupture test data. So this is a incremented 50 Fahrenheit increase in temperature. So this line is governed by the tensile stress multiply 3.5 for the allowable stress. And high temperature area, this area is from here, from this point, the creep region area. So now this is dotted table, dotted profile, but I assign the drawing the line. So so look at the continuous allowable stress value. This actually the dotted 50 deg Fahrenheit incremented dotted line is indicating the allowable stress temperature curve. So that inflection point here, this is for something the key point. So inflection point plus 50 Fahrenheit temperature here is a start point. We assumed a start point of creep region as the temperature increasing by 50 Fahrenheit from inflection point. So we understanding. So the start point of the creep region here. If we find the inflection point. Here we discuss about the method of establishment of allowable stress values in ASME Section 2 Part D. So here is indicated of the description of the allowable stress values establishment taken from ASME Section 2 Part D. So 100 derivation of allowable stress values. The values in Table 1A and 1B. Table 1A for ferrous material allowable stress value, and Table 1B for non-ferrous material allowable stress value list are established by the committee only. In the determination of allowable stress value for materials, the committee is guided by successful experience in service insofar as evidence of satisfactory performance is available. Such evidence is considered equivalent to test data where operating conditions are known with reasonable certainty. So here is a nomenclature, and the maximum allowable stress shall be the lowest value obtained from the criteria in Table 100. I assign the Table 100 here. The mechanical properties considered and the factors applied to establish the maximum allowable stresses are as given below here, paragraph A and B. Paragraph A for allowable stress value for temperature below the creep range. Paragraph B indicated allowable stress value at the temperature in the creep region. A, at temperature below the range where creep and stress rupture strengths govern the selection of stresses, the maximum allowable stress value is the lowest of the following. The following the number 1, 2, 3, 4. Number 1 and number 2 for related tensile strength level. Tensile strength divided by 3.5. So number 1 is for room at the room temperature, and number 2 is at temperature. So number 2, the tensile strength at temperature divided by 3.5. Number 3 and 4 related on yield strength level. So 2/3 of the specified minimum yield strength at room temperature for number 3. Number 4, 2/3 of the yield strength at temperature. But in the application of these criteria, the committee considered the yield strength at temperature to be SYRY. SY is mean here specified minimum yield strength at room temperature. The RY is a ratio of the average temperature dependent trend curve value of yield strength to the room temperature yield strength. And the tensile strength at temperature to be 1.1 ST means the specified minimum tensile strength at room temperature. RT is the ratio of the average temperature dependent trend curve value of tensile strength to the room temperature tensile strength. So that ASME section 2 part D is indicated something like this factors to be considered. But here we discuss about the allowable stress value below the creep temperature range, below the creep temperature. So number 1, 2, 3, 4. We considered about the number 1, 2, 3, 4 only. Not consider the SYRY and 1.1 STRT. So now paragraph B, at temperature in the range where creep and stress rupture strength govern the selection of stresses, the maximum allowable stress value for all material is established by the committee not to exceed the lowest of the following. So three types of the creep rupture test data indicated. Number 1 is 100% of the average stress to produce a creep rate of 0.01% per 1,000 hour. So number 2 is 100 average percent of the average stress to cause rupture at the end of 100,000 hours. Number 3 is 80% of the minimum stress to cause rupture at the end of 100,000 hours. So FABG is indicated here. The multiplier applied to average stress for rupture in 100,000 hours at 1500 deg Fahrenheit and below, FABG equal 0.67. So number 2 indicated that 67% of the average stress to cause rupture at the end of 100,000 hours. My familiar with the method is rupture stress test is number 2 like this. So 100,000 hours is been around 11 years. It is hard to conduct the creep rupture test during the 11 years. It is hard. It is very hard. So normally the conducted relatively higher stress applied and short time duration rupture test. Obtained some data and estimated 100,000 hour duration to be considered rupture stress. So I will talk about the creep rupture test with later video. Two sets of allowable stress values are provided in Table 1A and 1B for austenitic stainless steels, nickel alloy, copper alloy, and cobalt alloys having an SY bar STE ratio less than 0.625. SY bar STE ratio is equal yield ratio. The austenitic stainless steel and nickel alloy is always almost have 40% of the yield ratio. So austenitic stainless steel and nickel alloys have always two sets of allowable stress value in the table 1A and table 1B. So the higher alternative allowable stress are identified by a footnote to the tables. These stresses exceed 2/3 but do not exceed 90% of the maximum yield strength at temperature. So 90% of the minimum yield strength. This is in design condition very concerned about the safety concern. So we offer something to the plastic deformation. So that we something caution to using a higher alternative allowable stress value. So the comment is the higher stress values should be used only where slightly higher deformation is not in itself objectionable. These higher stresses are not recommended for the design of flanges or other strain-sensitive applications. So I commented related on the yield ratio of the material. Yield ratio 60%, 50%, 40%. And in case of if we assign the TS equal 1.0, so 3 divided by 3.5, TS multiply 1 3.5, so safety factor 3.5, so TS multiply 1 3.5. So in case of the TS is 1.0, so 1 divided 3.5, 0.857 factor multiply 0.857. So how about yield strength? Yield strength in case of the yield ratio 60%, yield ratio equal 0.6, and yield ratio 50%, so yield strength 0.5. Yield ratio 40%, yield strength 0.4, so multiply 2/3. This is 2/3 of the yield strength. So multiply 2/3 value, obtained value 0.4, 0.333, 0.2666. So which one is lowest value something? So normally thinking ferritic material has almost ferritic material has a yield ratio 60% to 50% to 60%. So austenitic stainless steel and nickel alloy have almost 40% yield ratio. So for ferritic steel, in case of ferritic steel, TS tensile strength multiply 1 3.5 is always lower value than yield strength multiply 2/3. So allowable stress value below the temperature of the creep region is tensile strength multiply 1 3.5 is the govern dominate the allowable stress value. So in case of the austenitic stainless steel and the nickel alloy, is always govern the allowable stress value below creep region is yield strength multiplied to third is dominated values for allowable stress values. So tensile strength multiply 1 3.5 tend to dominate the allowable stress values below temperature of creep region for ferritic steels, which have 90% to 60% of yield ratio. Yield strength multiplied to third tend to dominate the allowable stress value below temperature of creep region for austenitic stainless steels and nickel alloys, which have 40% of yield ratio. So table 100 and 100 tables. This is a criteria for the summarizing, establishing the allowable stress value. So wrought and cast ferrous and non-ferrous material is tensile room temperature above room temperature. Tensile strength much divided by 3.5. Yield strength is yield strength multiplied to third. And this is a stress rupture test. This is 67%. This is 80%. This is number ones, 0.01% per 1,000 hours. How about welded pipe? This is a wrought material, cast material. No welding. No welding pipe. So how about a welding pipe? Welded pipe or tube, ferrous and non-ferrous. So this table indicated if we use a welded pipe, 0.85 factor to be multiplied like this. Next, we will discuss about why does a coefficient of Y have a different temperature dependence for each type of materials. Allowable stress temperature curves for the ferritic steels. In case of ferritic steels, value of Y is 0.4 and constant and below 900 degrees Fahrenheit. Next change to 0.5 at 950 degrees Fahrenheit. Then change it to 0.7 and above 1000 degrees Fahrenheit. And the key factor of determination of wall thickness by the calculation is allowable tensile stress. It is talked that the allowable tensile stress rapidly decreases in high temperature creep region, and also value of Y varies to increase to be able to calculate thinner wall thickness in high temperature creep region. The start temperature of the creep region can be identified to 900 degrees Fahrenheit at the branch point with the allowable stress temperature curves, which are plotted including tensile strength multiply 1/4 and tensile strength multiply 1/3.5, as shown in the figure for P22 pipe materials. Just before we look at this chart of allowable stress temperature curve for P22 material. So indicated two influence of the tensile strength. So current version is a safety factor of 3.5 of tensile strength, and before safety factor is 4 of tensile strength. 1998 version, before 1998 version. So two curves indicated. So higher temperature area is dominated by the creep rupture stress data to the allowable stress value. So creep test data is not changing. Initially assigned, not changed. So tensile strength factor is changing. So we can easily identify the start temperature of creep region at a branch point from this chart. So allowable tensile stress is determined based on creep rupture test data over 900. We can easily find this start temperature of creep region. I wondered if the same results on the start temperature of the creep region in cases of the other materials of the ferritic steels would be evaluated with the allowable stress temperature curves. The plotted curve of the allowable stress temperature for some representative ferritic steels as carbon steel pipes SA106 grade B, 1.25% chrome, 0.5% molybdenum alloy steel pipe P11, 2.25% chrome, 1% molybdenum alloy steel pipe P22, and 9 chrome percent, 1% molybdenum vanadium alloy steel P91 type 1 pipe material are shown in the figure 541. Here, this is a four ferritic materials allowable stress temperature curve indicated. So yellow line curve indicated the P91 type 1 allowable stress temperature curve. So gray line indicated P22 pipe material allowable stress temperature curve. And orange line curve is indicated P11 pipe materials allowable stress temperature curve. So blue line indicated the carbon steel pipe SA106 grade B, like this. So allowable stress temperature curve is different for each ferritic materials. So P22 we have already understanding the starting point of the clip region area is 900 degrees Fahrenheit. So, same as the indication of the ASME B31.1 specified Y factor. So 900 up to 900 degrees Fahrenheit. ASME B31.1 specified Y equals 0.4 assigned Y factor. And then increasing temperature 50 degrees Fahrenheit, 950 degrees Fahrenheit, Y factor is changing the Y equals 0.5. And next to high 50 degrees Fahrenheit temperature, 1000 degrees Fahrenheit, Y factor changing to the 0.7. And increasing in temperature, Y equals 0.7, constant value assigned. How about carbon steel pipe? Carbon steel pipe like this manner. So inflection point may be here. So lower temperature than 900 degrees Fahrenheit. And P11 pipes profile indicated inflection point here. Inflection point is around 900 degrees Fahrenheit. So that P11 of the starting temperature of the clip region is around 950 degrees Fahrenheit start point. So also P91 type 1. P91 type 1 is also ferritic steel. So that maybe the inflection point like this here. So we assume that inflection point is 1000 degrees Fahrenheit temperature for the P91 type 1 materials. So we assume that starting temperature of the 1050 degrees Fahrenheit is the start point of the clip region area. So something different profile of the arrow of stress temperature curve. So something difficulty to understanding the which start point of the clip region area for each materials. So inflection point identified on the plotted curves. However, it is not clear that which inflection point indicated in each allowable stress curve is identified to the clip region related in value of Y factor for ferritic steels. Allowable stress temperature curves along with curves of the tensile strength multiply 1 3.5 and the yield strength multiply 2/3. Determination of the allowable tensile stress is needed to be considered below 3 factors for the ferritic steels. 1 3.5 of tensile strength and 1.5 of yield strength. Clip rupture stress in clip temperature region. which one has a smaller value is determined for arrow of stress. If the determined arrow of stress is plotted against the temperature, its curved line normally indicates an inflection point or intersection between curves of 1/3.5 of tensile strength or 1/1.5 of yield strength and creep rupture stress. It is understood that the inflection point of the curve of arrow of stress temperature may indicate the separated border between influence of the tensile strength or the yield strength and influence of the creep strength. Verification of start temperature of creep region on ferritic steels. It becomes more clear understanding of the starting temperature of the creep region that the inflection point can be identified on the curve of the arrow stress, which is shown along with curve of the 1/3.5 of the tensile strength and the 1/1.5 of yield strength as indicated in figure 5411. This is for ferritic materials allowable stress temperature curve including with the yield strength and tensile strength curve. This is a 10B, 106B carbon steel pipe and P11 and P22 and P91 type 1. So in case of carbon steel pipe, so orange line indicated yield strength multiply 1/1.5 stress curve. And the blue line indicated tensile strength multiply 1/3.5. So in case of the carbon steel, inflection point here 650 deg Fahrenheit. So 650 deg Fahrenheit and below our stress value is dominated by the tensile strength multiply 1/3.5. So the curve is tensile strength multiply 1/3.5 and allowable stress is same same curve is indicated. So this temperature inflection point or more, so the rapidly decrease of the allowable stress value. So this higher temperature area influenced by the creep rupture test data to the allowable stress values. So we assume that start point of the creep region temperature around 650 deg Fahrenheit plus 50 deg Fahrenheit. 700 deg Fahrenheit is to be assumed starting point. So P11 pipe material. So blue line indicates the tensile strength and the orange line indicated the yield strength. So up to temperature 300 deg Fahrenheit, tensile strength multiply 1/3.5 is dominate to the allowable stress values. And after this temperature, increasing temperature. So yield strength multiply 1.5 dominate to the allowable stress values. So the inflection point indicated around 900 deg Fahrenheit, indicated here. So this point increasing the temperature rapidly decreasing the allowable stress value. This allowable stress in a higher temperature area is dominated by the clip rupture test data. So we assume that 900 deg Fahrenheit, 950 deg Fahrenheit temperature is the starting point of the clip region for the P11 type materials. So P22 pipe material, this is always look at the allowable stress temperature curve. So we understood that the inflection point 850 deg Fahrenheit and the starting point of clip region at 900 deg Fahrenheit is we have already understood. So up to the temperature 850 deg Fahrenheit, so tensile strength multiply 3.5 has dominated to the allowable stress values. So this is a P91 type 1 material. And P91 type 1 material is a relatively new introduced material, so that apparently the yield strength is very, very high level than other ferritic steel material. So the gray curve for allowable stress and blue line the tensile strength. So up to temperature 1000 deg Fahrenheit. So tensile strength multiply 3.5 dominate to the allowable stress. So tensile strength multiply 3.5 and allowable stress value is completely same up to temperature 1000 deg Fahrenheit. So over the temperature 1000 deg Fahrenheit, rapidly decrease of the allowable stress value. So we assumed the starting point temperature of clip region is 1050 deg Fahrenheit. So apparently the each material is different of the starting point of clip region. But the P22 is only same as the specified ASME B31.1. So A106 grade B inflection point 650 deg Fahrenheit. Start point of clip region equal inflection point plus 50 deg Fahrenheit equal 700 deg Fahrenheit. So we assume y equal 0.4 up to 700 deg Fahrenheit. P11 inflection point 900 deg Fahrenheit. Start point of clip region equal inflection point plus 50 deg Fahrenheit equal 950 deg Fahrenheit. So we assume y equals 0.4 up to 950 deg Fahrenheit. So P22, this inflection point 850 deg Fahrenheit, start point of clip region equal inflection point plus 50 deg Fahrenheit equal 900 deg Fahrenheit. y equals 0.4 up to 900 deg Fahrenheit. P22 data is completely matching, aligned with table 104.1.2-1. P91 type 1, inflection point 1000 deg Fahrenheit, start point of creep region equal inflection point plus 50 deg Fahrenheit equal 1050 deg Fahrenheit. We can assume y equals 0.4 up to 1050 deg Fahrenheit. So, in case of carbon steel pipe of A106B, start temperature of creep region of 700 deg Fahrenheit is estimated in figure 54105. So, here. It is understood that Y factor on the wall thickness calculated equation in ASME B31.1 is still assigned to 0.4 in creep region on A106B carbon pipe. That calculated wall thickness may be thicker than normal in creep region, since allowable stress is rapidly decreased in creep region. Figure 5412 shows the comparative curves of the calculated wall thickness, phase temperature with assigning both Y factors specified by ASME B31.1 and estimated by the curve of the allowable storage temperature for SA106B pipe. This is a comparative curve, calculated thickness pipe. So, horizontal axis indicate the temperature, unit of Fahrenheit, and the vertical axis indicated the TM, calculated thickness, inch unit. As assumption of calculation condition, TM equal PDO. There is outside diameter and denominator like this data. So we use seamless pipe. And pressure, internal pressure, design pressure P equal 7000 psi. Outside diameter DO equal 5-inch. Material carbon steel SA106B. Allowable tensile stress sigma A. And taken from data ASME B31.1. Safety factor 3.5. So blue line indicated value. We use value of Y specified by ASME B31.1. So 900 deg Fahrenheit Y equals 0.4. So we still use this equation Y equals 0.4. So calculate the thickness like this. So blue line. So this red line indicated the value of Y estimated by the curve of allowable tensile stress phase temperature. So Y equals 0.4 up to 700 deg Fahrenheit. And Y equals 0.5 at 750 deg Fahrenheit. And 800 deg Fahrenheit over Y equals 0.7. So, but carbon steel pipe is limited for temperature. So temperature limit is 800 degrees Fahrenheit for carbon steel. So I stopped the plotted increase the temperature. So up to the 800 degrees Fahrenheit is I plotted. But specify the value of Y factor to be used for the something thicker calculated wall thickness obtained. So I think that some things safety safety area I think. Not I think it is okay something. The calculated wall thickness with Y factor of 0.4 up to 900 degrees Fahrenheit by ASME B31.1 result in 20% greater than the calculated thickness with estimated Y factor of 0.7 at 800 degrees Fahrenheit, which is temperature limitation of carbon steels. However, I think that the calculated thicker wall thickness is better for safety reasons. In case of P91 type 1 of 9% chrome, 1% molybdenum palladium steel, start temperature of creep region of 1050 degrees Fahrenheit is estimated in figure 5411. Here. The calculated wall thickness with applying of Y factor of 0.4 up to 900 degrees Fahrenheit, 0.5 at 950 degrees Fahrenheit, and 0.7 at above 1000 degrees Fahrenheit specified in ASME B31.1 may be a thinner thickness as shown figure 5413. This is a calculated wall thickness curve for the P91 type 1 materials. Assumption of calculation condition Tm is like this equation. We have to use the seamless pipe. And the internal pressure P equals 7000 psi, outside diameter DO equals 5 inch. Material 9 chrome, 1 molybdenum palladium steel, SS335, P91 type 1. Allowable tensile stress sigma A taken from ASME section 2 part D 2021 safety factor 3.5. So this is a two indicated curve. So blue line indicated the value of Y specified by ASME B31.1. So Y equals 0.4 up to 900 degrees Fahrenheit. So here Y factor 0.4 using the up to the 900 degrees Fahrenheit, and next increasing the 950 degrees Fahrenheit, Y factor changing 0.5, and next increasing 50 degrees Fahrenheit, 1000 degrees Fahrenheit, Y factor changing the Y equal 0.7, and the temperature or more, Y equals 0.7 to be used like this. So red line indicated the value of Y estimated by the curve of R of tensile stress phase temperature. So Y equal 0.4 up to 1050 deg Fahrenheit. This is to be used for list of the Y equal 0.4, and next increasing the temperature 1100. This changing the Y equal 0.5, and next increasing the temperature 11 and 50 and Fahrenheit, the Y equals 0.7, and Y equals 0.7 to be used here. So apparently different calculated wall thickness. So if we use the specified value of ASME B31.1, so calculated wall thickness is thinner wall thickness calculated than its estimated Y value. So something we have, I think that the temperature area is thinner or thickness to be calculated. So some have a risk problem. So CSEF steel pipes, such as P91, are relatively new introduced materials for high temperature steel application, which also belong to the ferritic steels. They have high temperature creep resistant properties, and they are often used in high temperature steel line at around 1000 deg Fahrenheit to 1150 deg Fahrenheit. It is assumed that the calculated wall thickness of the CSEF steel pipes at that high temperature region tend to be thin, with underestimation in accordance with the specified Y factor in table 104.1.2-1 in ASME B31.1. This is a result of the Y factor value. So the obtained from the aerostory temperature curve. A106B is up to the 700,000. P11 950, and P20 is as same as ASME B31.1, and the P91 type 1 is very different of the specified Y value, 1050 deg Fahrenheit, like this. Next, we will discuss about allowable stress temperature curves for the austenitic stainless steels. In case of austenitic stainless steels, value of Y is 0.4 in a constant and below 1050 deg Fahrenheit. Next change to 0.5 at 1100 deg Fahrenheit, then change it to 0.7 and above 1150 deg Fahrenheit. The plotted curves of the allowable stress temperature for TP304 and TP316 as representative austenitic stainless steel as shown in figure 5421. two sets of higher allowable stress values and lower allowable stress values as commented description of the determination of allowable stress values at the temperature below the creep region in ASME Section 2 Part D are provided in this figure. So again, we look at the description of the allowable stress determination. Here, two sets of allowable stress values are provided in Table 1A and 1B for austenitic stainless steel. So, nickel alloy, austenitic stainless steel have a two sets of allowable stress value. So that figure 5421, this figure 5421, TP304 and TP316 are allowable stress temperature curve. So the lower curve is indicated for lower allowable stress temperature curve. So blue line indicates the TP304 lower allowable stress temperature curve. So gray line curve indicated for TP304 higher allowable stress temperature curve. So this point the over the temperature is a creep range areas. So below creep range temperature area, so higher allowable stress value and lower allowable stress values identified. So how TP316 lower allowable stress temperature curve indicated in the red line curve here. And the yellow line curve for TP316 higher alternative allowable stress temperature curve. So this temperature around 1150 temperature matching the higher and the lower allowable stress temperature curve is matching. So this curve, these allowable stress temperature curve indicated inflection point. Clearly we understood. So blue line curve for lower allowable stress for TP304. So inflection point is 1100 degrees Fahrenheit. And higher allowable stress temperature curve, gray curve, the inflection point at 1000 Fahrenheit. So higher allowable temperature curve and lower allowable temperature curve is a different indicator of the inflection point. Also 316 lower allowable stress temperature curve. So inflection point indicated 1100 degrees Fahrenheit. and higher allowable stress temperature curve, yellow curve, indicated 1050 degrees Fahrenheit, indicated the inflection point. So for allowable temperature, allowable stress temperature curve indicate different inflection point. So that TP304 inflection point at 1000 degrees Fahrenheit. So we assume the starting point of creep region at 1050 degrees Fahrenheit is assumed. So for our TP304, so this is same as the specified ASME B31.1. So higher allowable stress curve and lower allowable stress curve are indicated on TP304 and TP316. It is admitted that 1000 Fahrenheit inflection point and 1050 degrees Fahrenheit starting point of creep region on TP304 higher allowable stress curve are matching with the requirement in ASME B31.1. So inflection point and starting temperature of creep region can be identified on each curve for TP304 and TP316 as follows. TP304 higher allowable stress inflection point 1000 degrees Fahrenheit start of point of creep region equal inflection point plus 50 degrees Fahrenheit equal 1050 degrees Fahrenheit. So we assumed y equals 0.4 up to 1050 degrees Fahrenheit. TP304 lower allowable stress inflection point 1100 degrees Fahrenheit start point of creep region equal inflection point plus 50 degrees Fahrenheit in 1150 degrees Fahrenheit. So we assume y equals 0.4 up to 1150 degrees Fahrenheit. TP316 higher allowable stress curve inflection point 1050 degrees Fahrenheit start point of creep region equal inflection point plus 50 degrees Fahrenheit equal 1100 degrees Fahrenheit. So we assume y equals 0.4 up to 1100 degrees Fahrenheit. TP316 lower allowable stress curve inflection point 1100 degrees Fahrenheit start point of creep region equal inflection point plus 50 degrees Fahrenheit equal 1150 degrees Fahrenheit. We assume y equals 0.4 up to 1150 degrees Fahrenheit. It become more clear understanding of the starting temperature of the creep region that inflection point can be identified on the curve of the allowable stress, which is shown along with curves of the 3.5 of tensile strength and the 1.5 of yield strength on separately each material as shown in figure 542 for the lower allowable stress temperature curves. So 542.2 curve. This curve is lower allowable storage temperature curve for TP304 and TP316. So blue line indicated the allowable stress curve, the lower allowable stress temperature curve. So gray line indicated the yield strength multiplied 2/3 curve. So that 1100 meg Fahrenheit below and below the yield strength multiply 1.5 curve and allowable stress curve is a coincide matching. And this inflection point increase the temperature, rapidly decrease the allowable stress values. This is for this line indicated by the clip rupture test data. So orange line curve indicated the tensile strength multiply 3.5. So austenitic stainless steel is allowable stress decided by dominated by the yield strength multiply 2/3. Here is TP316 strain temperature curves for lower allowable stress. So blue line indicated lower allowable stress curve. So gray line curve for yield strength multiply 1.5 curves. So 1100 Fahrenheit temperature and below, the yield strength multiply 1.5 is a dominate to the allowable stress values. So over the temperature inflection point, so rapidly decrease of the allowable stress values. So the orange curve indicated the tensile strength multiply 3.5. So austenitic stainless steel is not influx of the tensile strength curve for decision of the allowable stress values. So it is understood that yield strength multiply 1.5 dominate the lower allowable stress values below temperature of creep region. Figure 5423 shows the higher allowable stress temperature curves along with curves of yield strength multiply 1.5 yield strength multiply 0.9 and tensile strength multiply 3.5 fifths on separately each material. So again, we look at the establishment of the allowable stress value in ASME section 2 part D. Here, so these stress The higher alternative allowable stress are identified by footnote the tables. These stresses exceed two-thirds of the yield strength, but do not exceed 90% of the minimum yield strength at temperature. So, not exceed 90% of the minimum yield strength at temperature. So we look at figure 5.4.3. This higher allowable storage temperature curve for TP304, TP316. So yellow line curve indicated yield strength multiply 1.5 curve. So blue line curve indicated allowable higher allowable stress temperature curve. So orange curve indicated yield strength multiply 0.9 percent 0.9 curve. So the gray line curve indicated tensile strength multiply 3.5. So yield strength multiply 0.9 influence to the decision of the allowable stress value below creep range temperature. So not the inflection point identified 1000 degrees Fahrenheit. So tensile strength multiply 3.5 and yield strength multiply 1.5 is no influence for the decision of the allowable stress values. TP316 curve also yellow line curve indicated the yield strength and the gray line curve for tensile strength curve. So blue line indicated the higher allowable stress value curves, temperature curve. So orange curve indicated the yield strength multiply 0.9. So also TP316 higher allowable strength temperature curve. So influenced by the yield strength multiply 0.9 curve is influenced. So easily we find the inflection point 1050 degrees Fahrenheit. So it is understood that yield strength multiplied by 0.9 dominates the higher allowable stress values below temperature of creep region. It can be assumed by figure 5.4.2.1 that the inflection point of 1000 Fahrenheit and the start temperature of the creep region of 1050 degrees Fahrenheit on the higher allowable stress curve of TP304 match table 104.121 in ASME B31.1. So summarize the table. So this line indicated specified by ASME B31.1. So in case of the austenitic stainless steel, so specify the temperature 1050 deg Fahrenheit and below or equal 0.4. So TP304 low allowable stress temperature curve indicated the start point of the creep region 1150 deg Fahrenheit, different the specified temperature. So TP304 high allowable stress temperature curve. So that 1050 deg Fahrenheit and below y equals 0.4, same as the specified ASME B31.1. So, and TP316 low alloy steel temperature curve, low allowable stress temperature curve. So that 1150 deg Fahrenheit and below temperature y equal 0.4 assigned. TP316 high allowable stress temperature curve 1100 deg Fahrenheit and below y equals 0.4. So next we talk about the allowable stress temperature curves for the nickel alloy N06690. In case of nickel alloy N06690, ASME B31.1 specify that value of y is 0.4 in a constant and below 1050 deg Fahrenheit. Next change it to 0.5 at 1100 deg Fahrenheit, then change it to 0.7 and above 1150 deg Fahrenheit, as same as austenitic stainless steels. The plotted curve of the allowable stress temperature for N06690 indicated in figure 5431 and figure 5432, it can be assumed that inflection point and starting temperature of creep region are identified on the allowable stress temperature curve as follows. Lower allowable stress curve, inflection point 900 deg Fahrenheit, start point of creep region equal inflection point plus 50 deg Fahrenheit equal 950 deg Fahrenheit. So estimated y equal 0.4 up to 950 deg Fahrenheit. Higher allowable stress curve, inflection point 900 deg Fahrenheit, start point of creep region equal inflection point plus 50 deg Fahrenheit equal 950 deg Fahrenheit. So estimated y equals 0.4 up to 950 deg Fahrenheit. So we look at the figure. So this is indicated for lower allowable tensile stress phase temperature curve for the nickel alloy N06690. So cold equal 690. So nickel alloy 29% chrome 9% ferrous. So, so this is this allowable stress temperature curve. We have clearly understanding the starting inflection point and starting point of the creep region. Here, this inflection point is 900 deg Fahrenheit. So 900 Fahrenheit plus 50 deg Fahrenheit is indicated the starting temperature of creep region, 950 deg Fahrenheit. So this is y equals 0.4, 0.5, y equals 0.7. This is a specified temperature region for about the y factor by the ASME B31.1. So this curve from this like this here is creep region areas. So this materials is like this 1100 temperature, maybe the creep region areas. So ASME B31 point assigns the 0.4 temperature, 1050 deg Fahrenheit. From the according to the allowable tensile stress temperature curve. So something higher temperature indicated by the ASME B31.1. It is indicated that the specified temperature of 1050 deg Fahrenheit for value of y equals 0.4 in ASME B31.1 is higher than the estimated starting temperature 950 deg Fahrenheit of creep region according to the allowable stress temperature curve for L069T. So next is along with indicated higher allowable stress temperature curve. The orange line indicated the higher allowable stress temperature curve. And the blue line is the lower allowable stress temperature curves. So this dotted line is ASME specified Y value areas. So this is a more clear understanding to identify the starting temperature of creep region at 950 deg Fahrenheit. For higher allowable stress or also lower allowable stress. This branch point is indicated the starting point of creep region. So inflection point is also clear, we understood. So the estimations of Y values do not match table 104.1.2-1 in ASME B31.1. So it becomes more clear understanding of the starting temperature of the creep region that the inflection point can be identified on the curve of the lower allowable stress temperature, which is shown along with curves of the 1/3.5 of tensile strength and the 1/1.5 of yield strength, as shown in figure 5433. This is for low allowable stress temperature curve along with the tensile strength multiply 3.5 curve, and also yield strength multiply 1.5 curve. Orange line the yield strength curve, and blue line the tensile strength, and gray line indicated the allowable stress value. So inflection point 900 degree Fahrenheit. So this temperature 900 and below, the allowable stress value is dominated by the yield strength multiply 1.5. So nickel alloy have a tendency to have a lower yield ratio, around 40%. So that in case of the estimation or establishment of the allowable stress for the nickel alloy, so almost yield strength yield strength level is dominated by the allowable stress values. So it is indicated that yield strength multiply 1.5 dominates the lower allowable stress values below temperature of creep region. Here. It is understood that yield strength multiply 1.5 dominate the lower allowable stress values below temperature of creep region. Start temperature of creep region of 950 degree Fahrenheit is estimated in figure 5433. It is understood that Y factor on the wall thickness calculated equation for N06690 in ASME B31.1 is still assigned to 0.4 in even creep region up to at the temperature of 1050 degree Fahrenheit. It is assumed that the calculated wall thickness may be thicker from 1000 degree Fahrenheit to 1100 degree Fahrenheit, since allowable stress is already rapidly decreased in creep region as shown in figure 5432. So this is a result of the calculated wall thickness related curve. So assumption of calculation condition, wall thickness calculation equation Tm equal PDO dominate 2 sigma A plus PY. We use a seamless pipe. So internal pressure, design pressure P equals 7,000 psi, outside diameter DO equals 5 inch, material nickel alloy B617 N0 6690. Allowable tensile stress sigma A taken from ASME B31.1 to 022. Safety factor 3.5. So the blue line indicated the value of Y specified by ASME B31.1. So Y equals 0.4 up to 1050 degree Fahrenheit here. And the next higher 50 degree Fahrenheit temperature y equals 0.5 at 1100 degree Fahrenheit. And y equals 0.7 above and 1150 degree Fahrenheit. So red line indicated the y estimated by the curve of R over tensile stress curve. Y equal 0.4 up to 950. 950 here. So this is a y point 0.y equals 0.4. And next high temperature 1000 is the y equal changing the 0.5, and next changing the y.07, y point y equals 0.7, and over the 1050 degree Fahrenheit, the y equal 0.7, so something. So one thickness calculation result show the specified y value is for something heavier wall thickness calculated. So let's summarize temperature dependent parameter value y. So this is specified y value. So the up to 1050 degree Fahrenheit specified y equals 0.4. So lower of stress bar temperature curve and higher R of stress temperature, both same, and 950 degree Fahrenheit and below y estimate is 0.4. Next, we discuss about allowable stress temperature curves for the nickel alloys N06617, N08800, N08810, N08825. In case of nickel alloy, ASME B31.1 specify that value of y is 0.4 in a constant and below 1150 degree Fahrenheit. Next change to 0.5 at 1200 degree Fahrenheit. Then change it to 0.7 and above 1250 degree Fahrenheit. The plotted curves of the allowable stress temperature of the nickel alloy are shown in figure 5441, figure 5442, figure 5543, and figure 55444. So we look at the figure. This chart is indicated the low allowable stress phases temperature curves for materials N06617, N08800, N08810, N08825. So yellow line indicated the N08810 here, and the blue line is the N08825. So allowable stress value indicated 1000 degree Fahrenheit by ASME Section 2, Part D, 2021. So that N0825 nickel alloy material is can be used up to the 1000 degree Fahrenheit. Over 1000 degree Fahrenheit cannot be this material cannot be used for the pressure retaining parts. So orange line is N06617 like this, and gray line curve N08800. So dotted vertical line indicated the specified values temperature range. So nickel alloy for four materials y equals 0.4 assigned 1050 degree Fahrenheit and below y equals 0.4, and 50 degree Fahrenheit increase in temperature 1200 degree Fahrenheit y equals 0.5, and the next higher 50 degree Fahrenheit 1250 degree Fahrenheit and over there over temperature y equals 0.7 assigned. So for material allowable stress temperature curve is a different starting point. So another figure look at this for higher allowable stress value curve and lower allowable stress temperature curve. For this is a material N06617. Allowable stress temperature curves for higher and lower value in ASME B31.1 2022. So that ASME B31.1 temperature limit it specifies the temperature limit to the N06617 1200 degree Fahrenheit. So over temperature with allowable stress value taken from the ASME in section 2 part D 2021. So the higher allowable stress temperature curve is same as the ASME 31.1 up to 1200 degree Fahrenheit. So this curve is indicated inflection point at 1150 degree Fahrenheit for higher allowable stress inflation. So inflation point plus 50 degree Fahrenheit, we assume the starting point of creep region. And this temperature is 1200 degree Fahrenheit. So for lower allowable stress temperature curve, so that inflection point 1200 degree Fahrenheit for lower allowable stress curve, and 50 degree Fahrenheit higher temperature, 1250 degree Fahrenheit indicated the start temperature of clip region here. So next is the M08800 nickel alloy allowable stress temperature curve. Right side M08810 allowable stress temperature curve. So both higher allowable stress and lower allowable stress curve is indicated here. So inflection point of here at 1000 degree Fahrenheit for higher allowable stress temperature curve. So 50 degree Fahrenheit higher temperature, 1050 degree Fahrenheit temperature is the starting point of clip region. So how about the lower allowable stress temperature curve like this? So this inflection point temperature is 1050 degree Fahrenheit. So starting point of clip region at 1100 degree Fahrenheit. So how about the M08810 allowable storage temperature curve? The higher allowable storage temperature curve. So this point is the inflection point at the 1050 degree Fahrenheit, the inflection point. So 50 degree Fahrenheit increase in temperature, 1100 degree Fahrenheit is a starting point of the clip region for higher allowable stress. So blue line indicated the lower allowable stress temperature curve. So here, this is the inflection point at 1100 degree Fahrenheit. So 50 degree Fahrenheit temperature increasing, and 1150 degree Fahrenheit temperature is indicated the starting point of clip region. This is the allowable stress temperature curve for L08825 nickel alloy material. So red line indicates the higher allowable stress value. Blue line is indicated the lower allowable stress value. So ASME B31.1, the assign indicated the allowable stress value for M08825 is a temperature limit 800 up to 800 degree Fahrenheit only. Over 800 degree Fahrenheit is there is no allowable stress value indicated in ASME B31.1. So we understanding that that M08825 nickel alloy material can be used up to 800 degree Fahrenheit. We cannot use the over 800 degree Fahrenheit for pressure retaining parts. The allowable comment 1, the allowable stress values are assigned at the temperature up to 800 deg Fahrenheit in ASME B31.1-2022. Time-dependent properties such as creep rupture stress data are not indicated on N08825. So allowable stress temperature curve is not indicated time-dependent property creep rupture stress data means creep region area is not indicated. So that material is not developed for heat-resistant material. Only corrosion-resistant material developing something. So summarize N material, nickel material N06617, lower allowable stress temperature curve, inflection point 1200 deg Fahrenheit, start point of creep region 1250 deg Fahrenheit. We assumed y equals 0.4 up to 1250 deg Fahrenheit. So higher allowable stress temperature curve, inflection point 1150 deg Fahrenheit, start point of creep region to 1200 deg Fahrenheit. We assumed y equals 0.4 up to 1200 deg Fahrenheit. Material nickel alloy N08800, lower allowable stress temperature curve, inflection point 1050 deg Fahrenheit. Start point of creep region 1100 deg Fahrenheit. We assumed y equals 0.4 up to 1100 deg Fahrenheit. Higher allowable stress temperature curve, inflection point 1000 deg Fahrenheit, start point of creep region 1050 deg Fahrenheit, assumed y equals 0.4 up to 1050 deg Fahrenheit. So nickel alloy N08810, lower allowable stress temperature curve, inflection point 1100 deg Fahrenheit, start point of creep region 1150 deg Fahrenheit, assumed y equals 0.4 up to 1150 deg Fahrenheit. Higher allowable stress temperature curve, inflection point 1050 deg Fahrenheit, start point of creep region 1100 deg Fahrenheit, assumed y equals 0.4 up to 1100 deg Fahrenheit. Nickel alloy N08825, unknown inflection point and start point of creep region by the allowable stress temperature curve. It became more clear understanding of the starting temperature of the creep region that inflection point can be identified on the curve of the lower allowable stress phase temperature, which is shown along with curves of the 1/3.5 of tensile strength and the 1.5 of yield strength on the separately each material as shown in figure 5445. So this is a 5445 curves of lower allowable tensile stress phases temperature for nickel alloy N06617, N08810, and N08800 and N08825. So indicated tensile strength curve and yield strength curve. So gray line curve is indicated lower stress value. So yield strength match by 1.5 same as the lower stress curve. So yield strength match by 1.5 curves dominate to the lower stress values. And from this line, higher temperature area is dominated by the creep rupture test data. So inflection point here, 1200 deg Fahrenheit, and the starting point of creep region at 1250 deg Fahrenheit. Very clear understand. So this is a M0810 allowable stress temperature curve. This is tensile strength multiply 3.5 curve, blue line. No influence for the allowable stress values. So orange line indicated the yield strength curve, and the gray line indicated the allowable stress value. So the inflection point 1100 deg Fahrenheit. So below temperature 1100 deg Fahrenheit. So yield strength multiply 1.5 curve the dominate to the allowable stress values. So starting point of creep region at 1150 deg Fahrenheit. This chart is for M088800. So blue line is a tensile strength multiply 3.5. So tensile strength curve is no influence to the allowable stress values. So this curve is including the yield strength curve and allowable stress curve. So inflection point 1050 deg Fahrenheit, and 1100 deg Fahrenheit is the starting point of creep region. So M0825 is no indication of the creep region area by the allowable stress curve. So unknown starting point of creep region. So it is understood that yield strength multiply 1.5 dominate the allowable stress values below temperature of creep region. So this table is indicated the summarize of the nickel alloys time-dependent parameter value of Y specified table 104 1.21 and estimated by the allowable stress temperature curve. So this indicated ASME B31.1 specified Y value time-dependent chart. So 1150 deg Fahrenheit and below Y equal 0.4 specified. So N0617 lower allowable stress temperature curve So estimated the temperature. So 1250 temperature degree Fahrenheit, higher temperature than specified temperature. So higher allowable storage temperature curve is 1200 degree temperature. The still higher temperature than specified temperature. So N0880 lower allowable storage temperature curve, the 1100 degree Fahrenheit 0.4. This is lower than a specified temperature. And the N0880 higher allowable storage temperature curve, 1050 degree Fahrenheit, still lower temperature than a specified temperature. N0810 lower allowable storage temperature curve. This is estimated temperature for 1150. So this is a matching with specified temperature. So N0810 higher allowable storage temperature curve. So the 1100 degree Fahrenheit lower temperature indicated than specified temperature. So N0825 the both lower allowable storage temperature curve, higher allowable storage temperature curve is not shown in the creep region. So next is we discuss about the chemical composition of the nickel alloys N06690, N06617, N08800, N08810, and N08825. As described above, investigation of the start temperature of creep region on the allowable stress temperature curves for the nickel alloys, it is understood that the obtained temperatures vary depending on the grade of nickel alloys. Analyzing of the allowable stress temperature curve shows that all assigned nickel alloys in table 104.1.21 are not heat resistant materials for high temperature application, and some alloys specialize in corrosion resistance. The specified chemical composition for the related nickel alloys are indicated in the below table here. The volume of chrome content, which are indicator of property of heat resistance and corrosion resistance. So we look at the austenitic stainless steel and also nickel alloy. We focus on chrome content. Chrome content is influence of the heat resistance and also corrosion resistance. So this chrome content volume is reasonable values for corrosion resistance and heat resistant materials. it is said that volumes of carbon content have an influence on the high temperature creep resistant property. So another key element is carbon content. Carbon content is a very aspect of the corrosion property. So if we have application of the corrosion resistance application, so carbon content is the mostly reduce the carbon content. So understanding the carbon content here, 0690 and M08825 is carbon content is limited, 0.05 maximum carbon content. But another 3 nickel alloy is relatively higher carbon content is specified. So we understand that carbon content indicated higher carbon content specified. This material for heat focus on heat resistant materials to maintain the creep strength, creep strength in a high temperature area. So it is assumed that nickel alloys of N0619 and N0825 are intended for corrosion resistant alloys, and also they have relatively lower temperature creep resistance property since their carbon content are specified to lower value of 0.05% maximum. So M0690, we call the Inconel 690. And the M0617 is the Inconel 617. M08800, Inconel 800. M08810, Inconel 800H. M08825, Inconel 825. So M06690 is the start temperature of creep region equal 950 deg Fahrenheit for low allowable stress. So M06617 start temperature of creep region equal 1250 deg Fahrenheit for lower allowable stress. M08700 start temperature of creep region equal 1100 deg Fahrenheit for low allowable stress. M08810 start temperature of creep region equal 1150 deg Fahrenheit for lower allowable stress. M08825 up to 800 deg Fahrenheit temperature limit accordance with the allowable stress temperature curves in ASME B31.1 to 0 to 2. So assumed not heat resistant material. Here is a summary comparison table for Y values specified in ASME B31.1-2022 and estimated by temperature dependence of the allowable tensile stress in various materials. So ferritic steels in ASME B31.1-2022 specify the temperature 900 degree Fahrenheit and below, y equals 0.4, and next high temperature 950 degree Fahrenheit, 0.5 change, and next 50 degree Fahrenheit temperature 1000 degree Fahrenheit, and or more temperature y equals 0.7 specified. So we evaluated four materials in ferritic steel, carbon steel, P11, P20, and P91 pipe material. So P22 material for we estimated by allowable stress temperature curve. We have a result of the temperature same as the specified temperature 900 degree Fahrenheit and below, y equals 0.4 or something. The another material is so allowable stress temperature curve indicated some different of the temperature dependence y values. So P9 type 1 is a relatively new introduced material as a CSEF steel. So that very different of the temperature and the specified temperature. So in case of that, some differences. So actually, calculate the wall thickness value is tendency to thinner wall thickness calculated here. So austenitic stainless steel in ASME B31.1, it specified temperature 1050 degree Fahrenheit and below, y equals 0.4. So we have evaluated two materials, 304 and 316, and two sets of allowable stress temperature curve, low allowable stress temperature curve and high allowable stress temperature curve. So estimated resulted the temperature dependency temperature for 0.4. So that TP304 high allowable stress temperature curve indicated the result of the same as the specified temperature. So 1050 degree Fahrenheit and below, y equals 0.4. So another allowable stress temperature curve is something different. So nickel alloy N06690 B31.1 specified temperature for in 1050 degree Fahrenheit and below, y equals 0.4. This is the same as the austenitic stainless steel. But actually, we evaluated by the allowable stress temperature curve something different result. Estimated temperature 950 degree Fahrenheit and below, y equals 0.4 in both lower and higher allowable storage temperature curve. So, very different temperature is indicated. So another nickel alloy 4 materials were indicated in ASME B31.1. So specified temperature is 1150 degree Fahrenheit and below, y equals 0.4. So we also evaluate of the allowable storage temperature in lower and higher and for materials. So L08810 and lower allowable storage temperature curves indicated the temperature result 1150 degree Fahrenheit and below, y equals 0.4, same as the specified temperature. So next, we will discuss about the relatively new introduced temperature-dependent parameter values of y in case of ASME Section 1, 2025. ASME Section 1 for boiler-related construct standard. Introduced relatively new method of determination of temperature-dependent parameter values of y for the wall thickness calculation as indicated in the attached description of PG 27.4.6 derived from ASME Section 1, 2025. So indicated description of the PG 27.4.6 derived from ASME Section 1, 2025. So y equal a coefficient having values as shown. So this table indicates the value of T small td. T small td 900 Fahrenheit and below. In case of T small td 900 degree Fahrenheit below. So y equals 0.4. Design temperature 900 degree Fahrenheit and below. So 900 degree Fahrenheit. This is same as ASME B31.1 ferritic steels. And increasing the temperature 90 degree Fahrenheit, 950 degree Fahrenheit, y equal 0.5. And next 50 degree Fahrenheit higher temperature, 1000 degree Fahrenheit, y equal 0.7. And more temperature, y equal 0.7. This upper line indicated the same as the ferritic steel case in ASME B31.1 2022. So lower column indicated T small td larger than 900 degree Fahrenheit. So design temperature equal T small td or less, y equal 0.4, and 50 T small td plus 50 degree Fahrenheit, y equal 0.5, and td plus 100 degree Fahrenheit, y equals 0.7, and more, y equals 0.7. So Y factor indicated that like this method changing changing from the ASME B31.1 to 0.22. So I only check the ASME section 1 2025 relatively new version. So I'm not sure. I did not look at the ASME section B31.1 2025 version. I'm not sure the revise the one factor decision. I'm not sure. So anyway, section 1 already changing 2025 in 2025. So as shown in PG 27.4.6, T small TD equal the lowest temperature values. So in a note, small TD equal the lowest temperature value listed in the maximum allowable stress tables from section 2 part D. See note time-dependent properties for respective table, at which the allowable stress values are obtained from time-dependent properties. Values of y between temperature listed may be determined by interpolation. So small td, the lowest temperature values are described in respective allowable stress temperature tables of the relevant material. It is assumed that temperature of small td value indicate the lowest temperature of creep region, and y equals 0.4 is assigned at the temperature of small td or less. So far, what we have just told is that values of y are variable depending on the materials as shown in table 104.1.2-1 in ASME B31.1-2022, and the estimated values of y based on each allowable stress temperature curve of materials are different depending on the material properties in creep region. We try to provide more concrete examples for the introduced method of ASME section 1 2025 with reference to the allowable stress temperature curves in ASME section 2 part D 2025 for the assigned materials in table 104.1.2-1 in ASME B31.1. So here I write down interpretation. Small td is the lowest temperature value listed in allowable stress tables from ASME section 2 part D 2025, at which the allowable stress values are obtained from time-dependent properties. So time-dependent property, what is? Time-dependent properties means the allowable stress data for the creep region, which are obtained from creep rupture test. So vice versa, time-independent properties. Time-independent properties means the data values of tensile strength, yield strength, reduction value, or elevation, and so on. So time-dependent properties means creep rupture test data. Creep rupture test data is depend on lifetime. So time-dependent properties in so here. So the lowest temperature values means the start temperature of creep region on the arrow of stress. It is assumed that T small td indicates the lowest temperature of creep region, and y equals 0.4 is assigned as the temperature of T small td value or less. So here is I extract available storage data from table 1A and 1B. Table 1A for ferrous material, table 1B for non-ferrous material in ASME Section 2, Part D, 2025. So the ferritic steel, carbon steel, chromoly steel, non-chromoly steel. So seamless pipe 106 grade B, 335 P11, P20 something. So line number 14, 19, 39, 26 is indicated ferritic steel representative material. So here this is the ferritic steel, and P number, group number, and minimum tensile strength specified 415, and the minimum is 240. So now I only look at the metric unit in ASME Section 2, Part D, 2025, and also ASME Section 1, 2025, in metric unit standard. So Section 1, Section 3, Section 1 for boiler related. 3 is nuclear, and Section 8 and Division 1 for pressure vessel areas. So this is external pressure chart number something, and this is a note. A note is very, very important here. So red circle, red square indicated mean this is indicated T small td number. So SC106 grade B, the note indicated T1 indicated, and P11 T5 indicate of the T small td, and P22 T4 indicated in a T small td, and P91 type 1 T6 indicated the buyer as a T small td. So each allowable stress data table indicated T small td, the lowest temperature values indicate. So we have to refer this number for the calculate the wall thickness. So this is estimate stainless steel and the nickel alloy in here. So N0617 and 0691. So austenitic stainless steel and nickel alloy is assigned two set of allowable stress values, lower allowable stress value and higher allowable stress value. So here we indicate the two set of the allowable stress value for austenitic stainless steel and nickel alloys. So the allowable stress temperature curve is different assign the small td number, even though the same material. But allowable stress curve value is different, so has a different small td numbers. So lower column is indicated the allowable stress data. So line number assigned difference. So ferritic steel, austenitic stainless steel, and nickel alloys. This temperature. This is for metric unit. So temperature is centidegree Celsius, and unit is megapascal. Maximum allowable stress megapascal. So later I assigned the allowable stress temperature curve and evaluated the temperature dependence Y values. So on this page is indicated notes, time-dependent property. So note to table 1A for ferrous material in ASME section 2 part D, and the right side table is for non-ferrous material. This note time-dependent property. So T1 indicated carbon steel A106 grade B T1. So T1 is allowable stress for temperature of 370 degrees Celsius and above are values obtained from time-dependent properties. So time-dependent properties mean creep rupture test data. I think means time-dependent properties. So T1, T2, T3, T4, so here different temperature indicate. So also non-ferrous material, table 1B, note T1, T2, T3, 4. So different temperature, small TD temperature indicated. So the lower table is indicated time-dependent property for value of Y coefficient in ASME section 1, 2025, and ASME section 2 part D 2025. This is a sample. Sample is indicated here. So table 1A for ferrous material, T1 3170, and T4 408, and T5 550, 510 degrees Celsius. So T small TD values here. So 0.4, y equals 0.4 is so 370 and 480 is this is a comment, not comment. T is small TD 900 and below temperature. So Y equals 0.4, 900 deg Fahrenheit, 480. And Y equals 0.5, 950 deg Fahrenheit. So 370 and 480 indicated a T small TD, but Y dependent dependent time temperature dependent Y value indicated this one. So different temperature. So 900 deg Fahrenheit. This value is the same as the ferritic material on ASME B31.1 2022. And next higher 50 deg Fahrenheit, 950 0.5, and next higher temperature 1000 deg Fahrenheit, 0.7. So T5 is the allowable stress of temperature of 550 deg C and above value obtained from time-dependent property. So 510. So 0.4. And next high temperature of 50 deg Fahrenheit, 0.5. And next 50 deg Fahrenheit higher temperature, 1050 y equals 0.7 and changing. So T6 also 540 degrees Celsius. So for 0.4 or 540 degrees Celsius, 1000 Fahrenheit. T7 565 deg T7 565 degrees Celsius. 1000 and 1050 deg Fahrenheit, 0.4. So this indicated Y time-dependent Y value is this is for T small TD values indicated here. So actually we have to evaluate the using the allowable stress temperature curve. So estimated Y dependent time temperature dependent Y values. So this curve for ferritic steel. So SA106 grade B, P11, P22, three materials curve indicated. This is the allowable stress temperature curve. Blue line indicated the carbon steel, A106 grade B. So at inflection point 350 degrees Celsius for SA106B. So T small TD, the T1 indicate 370 degrees Celsius. So location here. So this is we understand that this temperature is for starting temperature of the creep region area. So estimated. So from this temperature and below 370, so Y equals 0.4. And so we understanding that. So this is a P20. P20 is a gray line curve. So inflection point here, 450 degrees Celsius. So T small TD T4 equal 480 C. So temperature located here. So we understanding that 480 temperature is indicated starting temperature of the clip region. So that orange line indicated the P11. So inflection point 475 degrees Celsius. So T5, P11, the T5 equal 510 degrees Celsius. So indicate the temperature located here. So we understand that 510 degrees Celsius indicated the starting temperature of the clip region. This is a P9 right side chart for P91 type 1. So this is a gray line yield strength curve, and tensile strength multiple 1 3.5, and the allowable stress curve is same as. And this is an inflection point. I assigned along with yield strength curve and tensile strength curve because of the allowable stress temperature curve only. In only the allowable stress temperature curve, it is hard to identify the inflection point. So I assign the tensile strength data and yield strength data including here. So easy to understand the inflection point. Inflection temperature 525 degrees Celsius. So P91 type 1 indicate the T6. T6 equal 540 degrees Celsius. So location of temperature area here. So we understanding. This 540 degrees Celsius is indicated the starting temperature of the clip region. Next is allowable stress temperature curves for austenitic stainless steel in ASME in section 12025. So left side chart for TP304 allowable stress temperature curves for higher and lower values indicated. And right side for TP316 allowable stress temperature curve. So for the TP304 higher allowable stress temperature curve indicated in red line. So inflection point at 550 deg for higher allowable stress on the TP304, and higher allowable stress curve stress value indicated T small TD equal T7. T7 equal 565 DC for high allowable stress. So inflection point 550 and T7 equals 565 dc. So up to the temperature 565 degrees Celsius. So y equals 0.4. And next high temperature increasing 25. So y equals 0.5 changing. So blue line indicated for lower allowable stress temperature curve. So inflection point here for at the temperature 600 degrees Celsius. So small TD number indicated T8 for lower allowable stress value in TP34 595 dc. So here. So inflection point and for T8 temperatures are almost same. So 316 material for a high allowable stress temperature curve, the red line indicated. So inflection point here to the 575 dc. And so higher allowable stress values in TP316 indicated T small td equal T8. T8 equal 595 degrees Celsius. So it is this we understand. T8 equal 595 dC is indicated starting temperature for clip region. So how about lower allowable stress temperature curve? Blue line indicates so inflection point at the 600 and T9 indicate the lower allowable stress values. So 620 degrees Celsius indicated. So located here. So we understanding T9 equals 620 degrees Celsius indicated the starting temperature of the clip region. This is for nickel alloy N06690. So blue line indicated the higher allowable stress temperature curve. Orange line indicated the lower allowable stress temperature curve. So inflection point is for high temperature allowable stress 475 degrees Celsius. So T11 specified and 480 degrees Celsius starting temperature. So inflection point 500 degrees and T12 specified and 510 degrees Celsius indicate starting point of clip region for lower allowable stress. So another nickel alloy. Next is for nickel alloy of N08800 and N08810. So left side N0880 nickel alloy. Right side chart indicated the N08810. So two set of the allowable stress temperature curve indicated here. Blue line for higher allowable stress temperature curve. And the red line indicated the lower allowable stress temperature curve. So the inflection point on the higher allowable stress temperature curve indicated 550 degrees Celsius. So inflection point. And T14 specified in a higher allowable stress value in N08800. So T14 temperature indicated 565 degrees Celsius. So we understood that temperature indicated the starting point of creep region for higher allowable stress values here. So red line indicated the lower allowable stress values. So inflection point here 575 degrees Celsius. And T15 indicating lower allowable stress values. T15 indicated 555 degrees Celsius. So this temperature we understanding starting point of creep region. Yeah. So N08810 allowable stress temperature curve. So blue line indicated for a higher allowable stress temperature curve. So inflection point of 575 degrees Celsius. And T15 specified in a higher allowable stress value in N08810. So T15 temperature indicated 595 degrees Celsius. So we understand this temperature is the starting point of creep region. So red line indicated for lower allowable stress temperature curve. So inflection point 600 degrees Celsius. So T16 specified and temperature 620 degrees Celsius indicated in the ASME section 2 part D. So this temperature indicated the starting point of creep region. This is 17. This like this result. And the N08825 allowable temperature curve is not indicated in standard, only temperature limit here. So not shown the creep region areas of allowable stress values here, not shown in the small td. So N08825 the table is not shown the T small td number. This table is indicating the summary comparison temperature dependence of Y values of the specified by PG 27.4.6 in ASME Section 1 2025 and the estimated Y values based on the allowable storage temperature curves in ASME Section 2 Part D 2025. So the Faraday scale and temperature. So carbon steel pipe SA106B indicated upper column is indicated estimated by allowable storage temperature curve in section 2 part D 2025 and second line indicated T small TD specified in PG 27.4.6 in SME section 1 2025. So allowable storage temperature curve indicated the starting point temperature is 370. Also, specified T1 equal 370 Celsius. So actually the 0.4 is here up to here, but PG 27.4.6 indicated here. So T small TD 900 Fahrenheit and below. In case of this, so Y equals 0.4, the design temperature 900 Fahrenheit and below specified. So that so the starting point of the temperature of the creep region area, so the specified 480 degrees Celsius. So and below the Y equals 0.4 specified. And next high temperature 0.5 and next high temperature 0.7. So that the actual allowable storage temperature curves indicated estimated temperature at something different. So this method for same as the ASME B31.1 Power Piping standard 2022, same as NORAS. So P11 pipe material, it estimated by allowable storage temperature curve. So identified 510 degrees Celsius and below Y equals 0.4. So the T5 510 degrees Celsius was specified, and same as the result, the specified value and the estimate value. So P22 also estimated value, temperature value equal 480 index Celsius. So specified temperature T4 equal 480 C. So the same result as we have obtained. So P91 type 1 is also same result obtained. So estimated value and specified value 540. Yeah. The austenitic stainless steel, if we have evaluated two materials, type 304 and type 316 SST. So they have two sets of the allowable stress values. So estimated by lower allowable stress temperature curve. So indicated estimated value, temperature value, then 620. So and below y equals 0.4 estimated. So that specified table T8 equal 595 degrees Celsius are specified for lower allowable stress values. So something different result. So how about the higher allowable stress temperature curve? So 565 degrees Celsius and below y equals 0.4 estimated. So the T7 equal 565 degrees Celsius here. So same result, the estimated value, temperature value, and the specified value, same result. So how about the 316 material? Lower allowable stress temperature curve, estimated 620. So specified temperature T9 equal 620. So same result we have obtained. So how about the higher allowable storage temperature curve? So 595 temperature and below y equal 0.4 and specified temperature T8 equal 595. So also same result we have obtained. So how about the nickel alloy N06990? So also nickel alloy have estimated two allowable stress temperature curve, higher lower allowable stress temperature and higher allowable stress. So lower allowable stress temperature estimated temperature 510 and below y equals 0.4 and specified temperature T12 equal 510. So 510 and below y equals 0.4. The same result. And higher allowable stress temperature curve 480 degrees Celsius and below y equals 0.4 and specified T11 equal 480 degrees Celsius for higher allowable stress value. The same result obtained. So another nickel alloy N06617, N08800, N08810, N08825. So N06617 lower allowable storage temperature curve estimated. So 675 degrees Celsius temperature and below y equals zero point 0.4, and the specified temperature for lower allowable stress value T18 equal 675 degrees Celsius. So same result with the estimated value. So also higher allowable storage temperature curve estimate 650 degrees Celsius and below y equals zero point 0.4, and specified small TD temperature T70 equal 650. So same result we have. So how about M0880 is a lower allowable storage temperature curve. The 595 degrees Celsius and below y equals zero point 0.4 estimated, and also specified temperature T small td T15 equal 595. So same result obtained. Also higher allowable storage temperature curve 565 degrees Celsius and below y equals 0 0.4. So specified T small td T14 equal 565. So same result is obtained. So M0810 nickel alloy, low alloy storage allowable storage temperature curve estimated 620 0 0.4, and the specified temperature T16 620. So also same result we have. So higher allowable storage temperature curve estimated 595 degrees Celsius and below y equals 0 0.4. So specified T small td T15 equal 595 degrees Celsius. The same result. So M0825 nickel alloy is so standard did not indicated allowable storage value for creep region. Only temperature around 540. So we have no obtained allowable storage value for creep region. So the standard specified limited temperature up to 540 degrees Celsius. We assign the y equals 0 0.4. So again, return here. Table 558 shows the summary temperature dependence of Y values of the specified by PG 27.4.6 in ASME Section 1 2025 and estimated by values based on the allowable stress temperature curves in ASME Section 2 Part D 2025. That table shows that the temperature dependence of Y values specified by PG 27.4.6 in ASME Section 1 2025 is in good agreement with the estimated values by respective allowable stress temperature curve for the representative materials. It is thought that this new method of determination of temperature dependence parameter values of Y as specified T small td temperature on each allowable stress data table is reasonable for the wall thickness calculation in high temperature creep region. So that's all I have today. So I will talk about strength reduction factors and calculate wall thickness for pipe and valve with the next video number 6. Thank you very much for watching.